Okay, moving right along. The last four addition reactions that we're going to look at in this packet of notes can all be classified either as oxidations or reductions. So it's time for us to take a look at what that looks like in the context of organic chemistry. So in general chemistry, you learned how to calculate oxidation numbers for various atoms and to determine whether a reaction was an oxidation or a reduction. And we can do that in OChem as well, but most of the time we don't really even have to. All we need to do is compare our starting material to the product, and what we're looking for is changes to the bonding to carbon. So changes in bonding to the carbon atoms. Okay, so let's define in that context what's meant by reduction and what's meant by oxidation, how we're going to be able to pick these things out. So in a reduction, what we can say is that there are going to be more carbon-hydrogen bonds and or fewer bonds between carbon and something we'll call Z, where Z is more electronegative than carbon in the product than there are in the starting material. So let me write all that out and show you an example. So in a reduction, there will be more carbon-hydrogen bonds and or fewer bonds between carbon and we'll call it Z, where Z is an element that's more electronegative than carbon. So there's fewer CH bonds and or more CZ bonds in the product than in the starting material. Okay, so let's look at an example. This is one we're going to see in a few pages. So if we have an alkene and we treat it with hydrogen gas and palladium metal, an addition reaction occurs where the hydrogen adds across the alkene. So each of the carbons in the alkene now is bonded to a new hydrogen. So what happened here is that we gained two CH bonds. Therefore, this is a reduction. And sometimes people abbreviate or signify reduction with a little h in brackets. Okay, now you might be noticing, well, the carbon-carbon pi bond also broke, so we lost that. But we don't care about bonds between carbons and other carbons, just bonds between carbon and hydrogen and carbon and things that are more electronegative than carbon. So that's an example of a reduction. An oxidation is going to be exactly the opposite of that. So in an oxidation, there are fewer carbon-hydrogen bonds and or more CZ bonds in the product than there are in the starting material. So that would be an oxidation. So let's look at an example of that. So let's say we have this guy. This is a primary alcohol. And we do a reaction that converts it to this aldehyde. So to analyze this, you may want to draw in the hydrogens that are not explicitly drawn in the starting material. And notice that the carbon that I'm highlighting in each of the structures is the same. So the highlighted carbon in the alcohol becomes the highlighted carbon in the aldehyde, which is the carbonyl carbon. So what we see is that we lost one of our CH bonds. So one of them is still intact, but the other one is gone. So we lost a CH bond. But also, in the product, we now have a carbon-oxygen pi bond, whereas we only had a sigma carbon-oxygen bond in the starting material. So we gained a carbon-oxygen bond, too. And that would be the pi bond. So those two factors together lead us to conclude that this is an oxidation. Which sometimes is abbreviated with a little O in brackets. Okay, so let's take a look at some examples of this and see if you can look at these examples and figure out what's going on. So I'm going to draw three sets of examples, or three examples rather. And then I'd like you to pause the video and see if you can assess each one as an oxidation, a reduction, or neither. In this third one, I'm going to give you reagents. So you're going to have to predict the product as well. Okay, so pause the video and see if you can do those three examples. Okay, so hopefully you have worked on those. So let's take a look at what you came up with. In the first example, we can see that we went from a carbon-oxygen double bond to a carbon-oxygen single bond. And so we lost a CO bond. We lost the pi bond. We also recognize that in the product, there's a hydrogen attached to a carbon that wasn't there in the starting material. So we gained a CH bond. So those two things together signify that this would be a reduction. In the second example, we lost a bond between carbon and hydrogen. So this bond right here is now gone. So we lost a CH, but we gained a CO bond. So in the product carboxylic acid, that's a new carbon-oxygen bond. So those two factors taken in concert signify that this would be an oxidation. Okay, now let's look at this final example. So mercuric acetate and water followed by sodium borohydride, hopefully you'll recognize as being what's called an oxymercuration demercuration. Which is a Markovnikov hydration, as you learned earlier in this packet. In this case, both of the carbons are equally substituted. So again, it's always helpful to draw in the hydrogens, even if they're not explicitly drawn in. If you need them to analyze things, by all means, draw them in. And so both of the carbons in this are equally substituted, which means that the OH group could attach to either one. So there's not going to be any preference, and you're going to get the same product regardless. So the two new bonds that you created were a CO bond, so you gained a CO bond, but you also gained a CH. So an increase in the number of carbon-oxygen bonds is oxidative, but an increase in the number of carbon-hydrogen bonds is reductive. And because you have one of each, this is neither an oxidation nor a reduction. So the take-home message there is that not all reactions can be classified as oxidations or reductions, but now we know how to classify the ones that can be. So let's take a look at a few more addition reactions. And we're going to spend the rest of this time in this video on epoxide formation and what we can do with epoxides once we form them. So for starters, for the addition reaction part of this, you can make an epoxide from an alkene in a reaction using what's called MCPBA or MMPP. Now those are both examples of what we call peroxy acids, which are also known by various other terms, such as peracids or percarboxylic acids. So you can think of this as a new functional group that you haven't seen. So what does it look like? Well, let's see over here on the left. I'm going to draw a couple of structures. So this structure is a carboxylic acid. This one happens to be benzoic acid. But a similar compound, instead of having an OH group, has an OOH group. That would be called perbenzoic acid. So that's an example of a peroxy acid. It has an extra oxygen where usually you have just one oxygen in that OH group. The structures of MCPBA and MMPP are shown down here, and so notice that they both contain that group, and the rest of it we can just think of as R. Okay, so in both cases, this and this, those pieces are not contributing or not participating in the reaction, so those are just R groups. So the reason why you might choose MCPBA over MMPP or vice versa would probably just come down to availability, solubility in different solvents that you needed to use, and so on. But they're going to do exactly the same thing in these reactions. Okay, so the mechanism is what we call a concerted mechanism. When we say that a mechanism is concerted, what that means is that it's happening all in one step. So all the involved bonds, that is, any bonds that are going to form or break in the reaction, are doing so at the same time. So all the involved bonds are forming or breaking at the same time. Meaning that the reaction occurs in one mechanistic step. So that's a concerted reaction. Now, the peroxy acid, when it interacts with the alkene, does so through what we call its reactive conformation. So that's also a new term. The reactive conformation is just the conformation that a molecule has to be in for a particular reaction to occur. All right, so to think about this, let's look at the structure of a peroxy acid. So I'm going to draw this over here, and then we'll draw the mechanism over on the left. I think we'll have enough room. Okay, so let's draw a peracid, like so. And what we can see is that because we have an atom with a lone pair next to that carbonyl, you can invoke some resonance. And the resulting resonance structure is going to look like this. What that does, or what the presence of this resonance does, is sets up an inductive effect. So if we look at these two oxygens right here, the oxygen with the positive charge is drawing electron density toward itself from the oxygen that has the hydrogen attached to it. That makes the oxygen with the hydrogen on it partially positively charged. And as it turns out, that's going to be the oxygen that gets attacked by the alkene. So the alkene attacks that oxygen, and that allows the weak oxygen-oxygen single bond to break toward the oxygen with the positive charge. So you get the additional benefit, or the benefit, of breaking a weak bond, which is an energetically favorable thing to do as long as you're trading it in for a stronger bond, which in this case you will be. Okay, so let's take a look at the reaction mechanism. Now we're going to draw the peracid in its reactive conformation. Like so. Remember, it doesn't matter which of those two peracids we use, so the R group is there just as a placeholder. So this is in the reactive conformation, and I'm going to draw an alkene right under it. Now the thing we want to notice about this conformation before we start drawing the mechanism is the following. There's an intramolecular hydrogen bond that exists between the carbonyl oxygen, which has this lone pair, and the hydrogen that's attached to that other oxygen. So that's holding this molecule in this conformation because it gives you a 5-membered ring, which has a particular stability associated with it. Okay, so this is not only the reactive conformation, but it also happens to be one of the major conformations of the peracid. Okay, so for this to happen in a concerted fashion, we're going to have to draw a number of arrows. So there are going to be 5 arrows, so I'm going to number them as I draw them and explain what's going on at each step. So the first thing is the pi electrons in the alkene attack this oxygen. We'll call that arrow 1. That causes the electrons between the two oxygens to move away, and so they're going to move over here. So they break and start moving toward the carbonyl oxygen. That causes the pi bond to break, so that's the third arrow. The carbonyl oxygen now formally bonds to this proton. So the hydrogen bond becomes a covalent bond, which means that the electrons that connect that hydrogen to the oxygen that was attacked first are now free to attack back at the alkene, one of the alkene carbons. So let's draw the result of that, keeping all the atoms in more or less the same positions that we started so we can see what ends up where. So we get the epoxide. So this O is this one. And then up above, we have this guy. So that, although it's a little hard to see because of the funny way that it's drawn, is a carboxylic acid byproduct. Okay, so when you make an epoxide in this way, or when you make any epoxide, when you do it using an addition reaction, the result has to be a syn addition, because what you're doing is forming a 3-membered ring. And so the 2 bonds from the carbons to the oxygen, we can't have one that's coming forward and one that's going back, because then they both would not be able to connect to the oxygen. So epoxide formation is a syn addition. Let's take a look at predicting a product. So we're starting with an alkene, and we recognize that the alkene is achiral. So it's optically inactive. We're using MCPBA, which is also, if you take a look at the structure up above, convince yourself that that's also achiral. So we have optically inactive starting materials. Which would lead us to suspect that we're going to get optically inactive product. So the epoxide can form from the front face or the back face of this alkene. It forms from the front face. That pushes the methyl group back. And if it forms from the back face, that pushes the methyl group forward. These are enantiomers. And as you've seen before, because in this case with an achiral alkene, there's no preference, an achiral alkene and achiral reagents, there's no preference for the reagent to attack the alkene at one face or the other. And so you're going to get an equal mixture, which, as you know, is a racemic mixture, and therefore optically inactive. All right, so now we know how to make epoxides. Well, as it turns out, epoxides are very, very useful in organic chemistry when we're making more complicated molecules through a process known as multi-step synthesis. So not just doing one reaction, but stringing a bunch of reactions together. Epoxides are not uncommonly used as important synthetic intermediates. So let's take a look, sort of a preview of what some things we'll do in the second semester. Let's take a look at a couple of things that we can do with epoxides. So the main thing that you would do with an epoxide is to open it. So you can open the three-membered ring. So let me draw a little picture up above. So here's an epoxide. It has a three-membered ring, and as you'll recall from conformational analysis, that is associated with a considerable amount of strain. If you have a nucleophile, the nucleophile can attack either of these carbons in the example that I'm giving you. So in both cases, now draw that, that's going to be cluttered. The bonds between the carbons and the oxygens are polarized. So you have partial positive charge on each of the carbons and partial negative charge on the oxygen. So a nucleophile can attack one of the carbons, and that's going to cause the carbon-oxygen bond to break. And so you get something like this. And then you can add in some acid. So we'll say H plus as an abbreviation for some acid. And protonate that alkoxide intermediate and get to this. So that's called opening an epoxide. So breaking one of the CO bonds to relieve the strain in the ring and make it not a ring anymore. So what we can do with an epoxide, one of the things we can do is to form something called an anti-vicinal diol. So let's take a look at what all of this means. Diols are just molecules that have two OH groups. So a diol is an organic molecule with two OH groups in it. And two important classes of these are called geminal and vicinal. A geminal diol is also called a hydrate. And what geminal means is that the OH groups are on the same carbon. By contrast, a vicinal diol, as shown to the right, the OH groups are on neighboring or adjacent carbons. So we're looking at making vicinal diols. Now we can do this in aqueous media, either under acidic or basic conditions. So the first thing that we have to think about when we're inspecting an epoxide is to look at the epoxide carbons and to determine whether they are or aren't equally substituted. So for example, in this case, with this epoxide, the carbon on the left, we could call that an epoxide carbon because it's part of the three-membered ring. That's more substituted because it's connected to more carbons. The other one, because it's connected to less carbons, is the less substituted. So we need to be mindful of the degree of substitution of each of the carbons in the epoxide, because depending on whether you're running the reaction to make the diol under acidic or basic conditions, that's going to dictate which of those carbons gets attacked by the nucleophile. So let's look at acidic conditions first. In acidic conditions, the epoxide gets protonated and water attacks the epoxide. So let's draw a mechanism for this. Actually, we can do this with the example down below. So let's take a look. Okay, so looking at the conditions here, it says we have sulfuric acid and water. Okay, so that is known to the fans as H3O+. Okay, so that's the business end of what you have there. So remember, anytime you have H3O+, you always have water. Even if it's not explicitly written, it's implied, because you can't have H3O+ without having water. Okay, so those are the things that you have to work with. So in the first step of the mechanism, let's draw in our H3O+. In the first step of the mechanism, remember that if you're in the presence of a strong acid, that means that you look for something to get protonated. So you're looking for something that's weakly basic. So the other thing that you have in the reaction mixture here is the epoxide. So that's your weak base. So the oxygen will use one of its lone pairs to pick up a proton from H3O+. In doing so, that oxygen accrues a positive charge. Okay, so what else do you have in solution? Well, as we said down below, you've got H3O+ and you've got water. So it's going to be the water that acts as a nucleophile. But notice what we have. We have a three-membered ring where one of the atoms is not carbon. It's a heteroatom, in this case oxygen. There's a positive charge associated with the ring, and the two carbons in the ring are not equally substituted. We've seen this before when we looked at opening things like bromonium ions or chloronium ions, or in the mechanism involving mercuric acetate. So the oxymercuration, demercuration mechanism is another place where we saw this. In such cases, you'll remember that the nucleophile attacks the more substituted carbon. So it attacks, I'm going to actually make that arrow a little bit better, because that's fairly horrible. Okay, so that's still horrible, but in a different way. So it attacks that carbon and breaks open the ring. Okay, now let's look up above where it says water, which is a weak nucleophile, attacks the more substituted epoxide carbon from behind the leaving group. Let's change behind to from opposite the leaving group. Okay, so behind, opposite, same thing, on the other side of the bond to the leaving group. Okay, as we've seen before. So in this case, the bond to the leaving group, which is that oxygen, is going back, which means that the water came in from the front. That's going to end up pushing this methyl group that I just highlighted as blue back. So what you get is the methyl pushed back. You have water attached, and then the other bond to the oxygen that was part of the epoxide ring stays the same. It's still going back. So that would be the green bond. And as we've seen in other situations like this, we're not done until somebody comes along and pulls off one of those protons on the oxygen that has the positive charge. Which, speaking of the positive charge, I'm going to redraw that so it's a little clearer. Okay, so remember that things that have positive charge associated with them are very, very acidic. Okay, as we saw briefly, we glimpsed that in the acid-base section. The strongest base that you have in solution is water. And it's also the one you have the most of. So that's going to deprotonate this intermediate. And that gives you the product. Which is a vicinal diol because it has two OH groups on adjacent carbons. And it's also anti because one is coming forward and the other is going back. Okay, so when you're opening an epoxide in aqueous acid, let's do a little summary here. In aqueous acid, protonate first, then the nucleophile attacks. Okay, let's see how that's different in base. If you're in aqueous base, then what you have going on is something like sodium hydroxide in water or potassium hydroxide in water. So it might be written in one of these forms. But in both those cases, the important part of what you have is the hydroxide ion. Remember that K and Na are spectators, and so they're not going to be participating in the chemistry here. Okay, so under basic conditions, we have a better nucleophile. Hydroxide is a good nucleophile. It's a much better nucleophile than water. And remember that nucleophilicity is a measure of how fast something reacts. So the hydroxide ion, because it's a better nucleophile, is going to attack where it can get to fastest. That's going to be at the less substituted epoxide carbon, but it's still going to attack from behind or from opposite the leaving group and open the ring that way. And then notice that we have two steps, the way this is set up. So step one, you subject the epoxide to hydroxide in water. And then in step two, after you wait a while, you're going to add in some H3O+. That's called an aqueous workup, or in this case, an aqueous acid workup. So we're going to label this as a workup. And then on the next page, we're going to talk exactly about what a workup is, because you're going to see a lot of different workups as you go forward in OChem 2. Okay, so let's draw a mechanism for this. So I'm going to redraw our epoxide. And let's draw the hydroxide ion over here. And so what's going to happen again, because the hydroxide is a pretty competent nucleophile, it's going to attack the place that it can get to the fastest, which is going to be the place that has the least amount of steric hindrance, the least amount of carbon shrubbery blocking the approach of the hydroxide ion. So it attacks the less substituted carbon, and the ring opens. When it attacks, it does so from opposite the bond to the leaving group. The bond to the leaving group, which is the oxygen in the epoxide, was going back. So the hydroxide came in, from our point of view, from the front. The bond to the other oxygen is still going back, and that oxygen picked up a pair of electrons from the carbon-oxygen bond that broke. So now it's O-, and then the methyl group is still in the same position. So all of that is step one from up here. At that point, you would add in the H3O+ to your reaction mixture. Oops. And assuming you don't overshoot the hydrogen, you're going to protonate that oxygen, and that delivers the product. So also an anti-vicinal diol. Okay, so let's do a little bit of a recap here. So that is step 2, which is the workup step. Okay, so in basic conditions, remember that the epoxide itself is only weakly basic. To get it protonated, you'd have to use a very strong acid like H3O+. So in basic conditions, there is no strong acid. The epoxide won't be protonated. In basic conditions in general, we want to think that things are going to get deprotonated. So if you're running a reaction under basic conditions, likely events are that things will get deprotonated and or you'll have nucleophiles attacking things, like we saw here. Okay, so in our first step, hydroxide, because it's a better nucleophile than water, attacks the less sterically hindered carbon in the epoxide. And that is because it can get to it faster. Okay, so let's look at a couple of other things before we wrap this up with a discussion of what a workup is. So let's say that we have this epoxide, and let's treat it with this combination of things. So you're looking at that and you're thinking, well, that is nothing like what we just talked about on this page and the last page. And you'd be half right. Okay, so it's not an aqueous reaction. It's not run in an aqueous medium. Instead, it's being run in methanol. But what I want to remind you is that alcohols and water have very similar chemical ways. Okay, so their chemical similarities are pretty extensive. And so whatever water would do in this case, an alcohol is going to do as well. TSOH, remember, is tossic acid. So this is a strong acid. So that's a strong acid. So what this means is that because you're running the reaction in acidic conditions, the epoxide is going to be protonated. And then the nucleophile will attack at the more substituted carbon. So because you have no water in here, but you do have methanol, it's going to be the methanol that acts as the nucleophile, attacks the more substituted carbon, opens the ring, gives you this intermediate, and then just like we saw with the acidic mechanism, that intermediate will get deprotonated to give us the product. Now, I didn't draw any stereochemistry associated with this mechanism, but it's going to be the same as we saw above and on the previous page. It's going to be an anti-configuration. So we'll say, yes, it is anti, but the stereochemistry is not shown. And in this case, we're not really getting a diol. We're getting something that you would call a hydroxy ether. Because you have an OH group and an ether in the same molecule. Okay, so one more question about this for you to think about. What if instead we wanted this outcome? Okay, so starting from the same epoxide, but instead of having the OH on the less substituted carbon in the product and the OCH3 group on the more substituted carbon in the product, we've reversed the regiochemistry. And so what we recognize is that there had to have been a bond here. Okay, so that was our original epoxide, was this part, meaning that OCH3 attacked the less substituted carbon. So let's make a note of that. So this was the less substituted epoxide carbon, which means that we ran the reaction under basic conditions. So in basic conditions, what version of methanol, if you will, would we use? Well, we would use the basic version. So we need to use the conjugate base of methanol. That's methoxide. So we could treat this with sodium methoxide, which by the way will be in methanol, followed by H3O plus workup. So the regiochemistry dictates the outcome. Oh, I'm sorry, the conditions dictate the outcome. The conditions dictate the regiochemistry of the outcome. Okay, so let's take a look at one more thing. What is a workup? Okay, so let's say you're doing a reaction. Okay, so a typical reaction that you would do in the lab, often organic chemists will use these little round bottom flasks. So let's say that you combine your reagents, whatever they are, in a round bottom flask. So you've got different things going on in there, and then you add the other thing, and so you have more things going on, and then they're swimming around in the solvent, they're meeting each other, they're reacting, it's all great. But to you, from the outside, it looks like a clear solution. It just looks like a little vial or a little flask full of water. So how do you know if the reaction is done? Okay, so one thing is if you're using a paper to follow, so you go to the chemical literature and you pull a paper and it says, here, this is how you do this reaction, and you run it for 1 hour and 3 minutes. Okay, then you have some sort of a guideline. But if you don't have that, then you're going to have to do some tests as the reaction is going on to determine whether or not it's gone to completion. Now, many of these tests involve lab things. Okay, so one of them is called thin layer chromatography. So thin layer chromatography, which is something that you'll learn about in the lab, is one way to tell what's going on in the reaction mixture, to tell generally what sorts of things you have there. Has product started to form? Has the starting material vanished? Has it been used up? So thin layer chromatography, or TLC, can help you assess that. You could also use what's called IR spectroscopy, which stands for infrared. Or NMR, which stands for nuclear magnetic resonance spectroscopy. So NMR works on the same principles as the MRI experiment that doctors do. So either of these, again, things that you'll learn about in the lab, we're not going to worry about the details here, can tell you what's going on in the reaction mixture. So you would just, in any of these cases, take out a very small amount of your reaction and then analyze it, and that's going to give you the information that you need. Okay, so let's say that you find out that the reaction is complete. using one or more of these techniques. Okay? In many cases, you're then going to do what's called a workup. And in a lot of cases, although not all of them, this is often aqueous. So you're going to add an aqueous solution to your organic reaction mixture. Now we've seen a bunch of reactions so far that are conducted in water or using water as reagents. And that's actually kind of uncommon in organic chemistry. Lots and lots of reactions and lots of chemicals, organic chemicals, are sensitive to water, and so you can't really use water as a solvent. So instead you'd be using some other organic solvent. Let's make a note of that up above. Let's say this is an organic solvent. So you would use an aqueous workup by adding an aqueous solution, and that could be just water. So water by itself, or it could be aqueous acid, or it could be aqueous base. It depends on the reaction conditions. So for example, if you're running a reaction and it's run under acidic conditions, then your workup is probably going to involve adding in some aqueous base so that you can neutralize the acid. By the same token, if you're running a reaction under basic conditions, then your workup is likely to be acidic, so aqueous acid. So one of the things that a workup will do is to neutralize the reaction mixture. The effect that that has, there's a couple of things. So first of all, let's take the example of opening an epoxide in aqueous base. Okay, so we had, I'm just going to draw a quick example of this. We had hydroxide, attack, the ring opened, that gives you an alkoxide, and then the H3O plus is the workup, and that gives you the product. Okay, so that's what we talked about previously. The H3O plus protonates that intermediate, so this alkoxide right here, but it also protonates all of the hydroxide that you still have hanging around in solution. So what that does is prevents any further reaction from happening. So we would say it quenches or stops the reaction. Okay, now another thing that it can do, especially if you're using an aqueous workup and you're pouring that in carefully to an organic solvent, what's going to happen is that the aqueous and the organic layers are going to separate from one another. So the aqueous and organic solvents will separate. So you're going to have two layers. Water and most organic solvents are not miscible. Now, there are a number of organic solvents that are miscible with water, but in general, we're talking about the cases where you would add in water or an aqueous workup to an organic solvent with which it's not miscible, which means that you're going to get two layers. Now, there's a special contraption in the lab called a separatory funnel that you would use to do this, which you may have seen, but we'll just think about this in a beaker. Okay, so you're going to have two layers. So a top layer, actually, let me draw this a little differently so it's clearer. So a top layer and a bottom layer. And depending on the density of the organic solvent, it could either be on the top or the bottom. Now, a lot of them are less dense than water, so they're going to float on the top. So let's just assume for this discussion that the organic layer is on the top, although it could be in either place. In the organic layer would be the products of the reaction, unreacted starting material, organic byproducts, things like that. In the aqueous layer, that's where any salts that form as byproducts in the reaction are going to end up. So any salts or ionic compounds that are byproducts end up here. Using the separatory funnel that I referred to earlier, you can separate the layers from each other, and so by so doing, you remove the salts from your reaction mixture. So it's a first step. The workup is a first step you can think of towards cleaning up the reaction mixture. Remember, when you run an organic reaction, you're typically after a particular product, and you want to get that product by itself. You want to isolate it. To do so, you've got to separate out all of the other crap that's associated with it. So this is the first step to doing that. You can get rid of the salts, and then the stuff that's left in your organic layer, you can evaporate the solvent, and then you can do a chromatography experiment where you can separate the rest of the things from each other and isolate the desired organic product. So then you would do some sort of separation, which is probably going to be chromatography. Doesn't necessarily have to be, but it's often that, to isolate the desired organic product. Okay, so to recap, oftentimes, but not always, a workup is aqueous. So you can either add water or aqueous acid or aqueous base to your organic reaction mixture once you've determined that the reaction is complete or has gone as far as it's going to go. Doing the workup, in many cases, neutralizes the reaction mixture. If you're running an acidic or a basic reaction, it's going to neutralize it. It can quench the reaction or stop it. And it can give you a first pass to cleaning up the reaction mixture. The other thing that we should mention here is that, as we saw up above, okay, in this example here, the reaction was not complete. We didn't have a neutral organic product until we protonated that intermediate. And so the workup in this case, and in other cases as well, completes the reaction. So let's add that to our list, that a workup might be essential to complete a reaction. And usually that's by protonating or deprotonating something. So we'll pick this up with the rest of the addition reactions.